There's Alexis. Oh, it was amazing. I could actually write on it. You weren't here with all the time I was trying to write on the board. It just wouldn't work. And I seriously was about to punch a hole. No. Okay, so I don't want to destroy school property. Okay, so there's a oh my, what was that for? Okay, so the original assignment was stapled. Okay, and so the back page is here. I'm trying to make sure that you understand how to read one of these diagrams. Today is essentially a work day, but there is a secondary paper here that goes along with it. So there's actually two different assignments that go with these diagrams. Okay, it's recording properly. I am presenting on thermodynamics. Okay. We're going to see if I can write on my board again. It worked yesterday. I don't know. We're about to find out. And I'm sorry if anybody's colorblind because I only have so many colors. So to read one of these, and this is the same thing that we had in our notes, whether it's an endothermic, and the way that you can tell immediately if it's endothermic or exothermic is, Brayden, do you have the larger uphill climb? If you do, it's endothermic, which is a positive heat value, or do you have the bigger downhill slope, which is an exothermic, which is a negative delta H, or heat of reaction? You use the red one over there. It's because that thing over there doesn't sharpen. I think somebody tried to sharpen it. I don't know. What? No. Today is essentially a work day, but I'm going to reanalyze one of these, which is the same thing that's over here. The one that's over here on the dry erase board, which those of you that are remote, I'm so sorry you can't see. This one's exothermic. This one's endothermic. We did. And so the thing that we're doing today is here, and it's being able to analyze what is the potential energy of the reactants, the products, the activated complex potentials, all three of those. What is the heat of the reaction, or the enthalpy, which is a delta H, and then what's also the activation energy. So it's not that it's hard, it's where are you subtracting from with these. That's the way that these things work. And it's been a very long time since I've done thermo. So over here, once again, and I'm sorry, those of you that are remote, so hope this is going to work again. This one's exothermic. This one's endothermic. And yes, you either have to put heat or energy into the system to make it work, or it releases heat from the system to make it work. If it's released, it's exo, which is the bigger downslope. Okay, if it needs to bring in energy to make it work, then the uphill, just think of the roller coaster. Going up to the top would be bigger if it's endo and it's positive. So if you, it's like I said, it's been a while since I've taught thermo. If it's bigger downhill, it's exo. If it's bigger uphill, it's endo. Okay, so you either have to, and I mean, some of you may have never ridden a roller coaster in your life, but to go up the hill, if there's more energy, you have to put the energy in to get to the top of the hill. Okay, so that's positive. Okay, and then if you're in exo, which is this one on the dry erase, if you're releasing energy, you're giving it off, and it's a negative delta H. And if you don't have the right sign, plus or minus, it's not right. Technically, if you don't have a negative, I will assume that it's positive. Okay, so We're about to see if I can write on the board. So your, well, it worked yesterday. Don't do that. Your potential energy for your reactants, which the paper that we have is, and this is not the one that's on here. I'm not answering the question that's on your paper today. It's going to be from, oh, it's working. Look, it's going to be from your baseline of the reactants to, we're going to call that 0. We called that 10. We called this 50. It's a 5. Your potential energy from your reactants will be from its baseline, okay, so where it starts, down to 0. That's how you know what your potential energy for your reactants. Your potential energy for your products, however, is from its baseline down to 0, which if I draw a dotted line and then I recalibrated my thing. So this would be what? 40? Let's say that's 40. I'm sort of estimating here. So your potential energy of your products is from its line down to 0. So this is your potential energy for your products. Your potential energy for what actually makes the thing happen in the first place is this hump all the way down to 0. So this would be your potential energy for your activated complex. Now, if I didn't mention this yesterday, because like I said, it's been literally 10 years since I've done this, if not more. You have to hit the tipping points, okay? And you've got some very unstable things going on before you start making products. But until you crest the top of this hill, you don't start making products. So the potential energy for your activated complex is from that hump all the way down to 0. Let's see what else. Let me change colors here. I'm sorry if anybody's colorblind. I'm not trying to pick on you, I swear. Your activation energy will be from the hump, the top of the hill, only to the reactants, not all the way down to 0, because you already started reactants. They already have energy. They have potential energy. That is your activation energy. And then your, once again, it's nice to be able to write on my board. I updated my software and it apparently made a big difference. Your heat of reaction or enthalpy, your triangle delta H, is the difference between your products to your reactants. And in this case, it would be 40 minus 10, which is 30 kilojoules. Okay, so what I'm letting you guys do today is to finish the one from yesterday. And the one that I have here on the board is the same thing as what's on the smart board. It's just that that's a endothermic. Bigger upslope is endo, positive delta H. Your bigger downslope, and I'm so sorry, those of you that are online, you can't see this. This one is exothermic, and your delta H is negative. And if you're basically looking at where are you starting and where are you going to? Okay, and in this case, I'm going down by 20, so it's negative 20. In this case, I'm going up by 40, 10, 30. So this is a plus 30. They're not hard, okay? It's just, I've learned in the multiple classes and years that I've taught that reading graphs is an issue. And I'm not quite sure why. But I'm giving you a chance to do yesterday's assignment and then also today's assignment and making sure that you don't have issues. All we're doing is subtracting. We're not doing anything else. We're not using any kind of formulas. But y'all, there's not much on this test. It's these things, and then it's calorimetry, which we're doing tomorrow. I don't know. My coworkers are going crazy. They were talking about calories and Cheetos the other day. It's just where is it asking? That's the hard part. Because all you're doing is you're subtracting. And you have to pay attention if it's endothermic, like the one that's on the board, you have a increase in heat, which is why it's positive. If it's exothermic, like the one that's on the dry erase board, which I'm so sorry y'all can't see it online, you have a decrease, which is why it's negative. That's the only catch, is which one is it doing. Let me double check and make sure none of you missed the test. Yes. What? Say that one more time. Okay. I don't know. Let's see. Okay, so your activation energy is from, no, that's fine. Okay, so your potential energy of the reactants is all the way here. Okay, so it's all the way across. Okay. Yes. And then this one's fine. And your activated complex is, okay, that one's fine. Your heat of reaction is your, okay, your heat of reaction is your difference between the reactants. So that one's not fine. So it's third right between the two. Yes. The only good sharpener I've got is right there. I'm sorry, what now? Okay, so this one is like the one that's on the board. Because it's exothermic. The downslope is sharper. So your potential energy of the reactants is from 0 to this line. So you're literally subtracting that to that. And that's going to be your value. Like it's, so wherever your reactant line is, your flat line where you start is your reactants. And you're going down to 0. To 0. And it's in kilojoules. It just depends. Where are you starting from? And then your potential energy for your products, which is normally the second thing that it asks for, is the ending flat line down to 0. Okay, so on yours, because it's not going to be what's up here, where does it start? Where does your flat line start at on yours for the reactants? Okay, and 30 minus 0 is, it's going to be 30 kilojoules. It's not, like, it's really not hard. It's not. It's just showing you what to subtract. It's not. It's just, and I mean, I personally hate thermodynamics because I don't teach it very often at all, but we ran into it. But no, you're literally just subtracting. So no, it's not hard. So your first flat line minus 0 is your potential energy of your reactants, and then the flat line at the end minus 0 is your potential energy of your products.
You're not subtracting, you just put what it goes.
Yeah.
Basically, well, it's the same thing. Yes, it's the same thing. And then your activate your potential energy of your activated complex. These unstable compounds that force the reaction to happen is the top of the hump minus 0.
So it really is just where the energy line is.
Pretty much. It's really not hard. You just don't know how to read these things. That's what today is for. Now, the only thing that's a little bit complicated is your activation energy, which is from your reactants up to the hump, okay? And then your heat of reaction or enthalpy, which is the difference between your reactants and your products, but not to zero.
Oh, so the types of reactions and products.
That's it. And if the downslope is more, it's negative. If the upslope is more, it's positive.
So this is good.
It's really not hard. It's just, you're not used to reading a graph like this at all. Yes. So the heat of reaction is, so when you go across, because I don't know which one you're doing, the difference between your reactants and your products, not zero and not the hump. Okay, now if the downslope is more, it's negative, and if the upslope is more, it's positive.
So, just one kg and it's one kilojoules. Oh my God, was that one too?
This is how do you call
This one is a
that?
10
Between the potential energy for the products is 10 kilojoules. The only thing that's positive or negative, everything's positive except for this. Because if the downslope's more, it's gotta be negative.
So it's a negative.
Exactly. But everything else won't have the only thing that might have a negative sign is this thing. Did I see another question?
Yeah, I mean,
Okay.
This is going to be a really long time since I've done it.
Okay, so you're done with the top one? You on this one? It's good. Okay, that's right. That's right. That's right. Heat of reaction is the difference between reactants and products, 30 minus 10. Oh, well, it's the difference between the. Heat of reaction is the difference between the reactants and your. What did you say something wrong? Yeah, the difference between the reactants and your products. So 30 minus 10 is what? No. The heat of reaction is the difference. So 30 minus 10 is how much? So that should be 20. And then your activation energy is the amount that it takes from the reactants to this pump. 40 minus 30 is, that's it. It's the same thing, rinse and repeat, roll. It's just, I mean, I don't know. You either have the larger uphill climb, which is going to give you a heat of energy that's positive, or you're going to have a larger downhill climb. Like I said, if it helps to think of it like a roller coaster, do it that way. But if the downhill slope is larger than the uphill, then this is a negative value. If the uphill slope is greater than the downhill slope, then this is negative, because you had to climb to get to here, which is why it's positive. With this one, you had to fall from here to here, you went down, which is why it's negative. Into this. So. It's, okay, the potential energy starts from nothing. It's not moving. Okay, so your potential energy is down to the baseline, which is 0. Okay, so your potential energy of your reactants is the first flat line down to 0. And then your, whether it's this one or that one, Your potential energy of your products would be from that last flat line down to zero. Your potential energy of this really unstable activated complex is from the hump down to zero. Okay, your heat of reaction is the difference between your reactants and your products. It doesn't matter if it goes down or if it goes up. It's the difference between the start, the true start, which is the reactants, to the true end, which is the products. You can get another paper if you need to. I normally have plenty of them. Let me check. Hold on. Let me do official attendance here real quick, and then I will go straight to you're done. Okay. And I still have to do the neutralization stuff and put that in. Fix my skates. The only thing that might be positive or negative would be delta H, the triangle H. We think if it's negative from where you started from to where you ended to, it went down, which is why it's negative. So if the downhill hump or the downhill part of the hump is more, then it's exothermic and it had to release energy to whatever, to the environment to do its job. So if the downside is bigger than the upside, this is negative. If the uphill is bigger than the downhill, then that's positive. Endothermics are positive and exothermics are negative.
So on the one from today, my active energy, or no, my heat of reaction would be negative.
Are you talking about the top one?
Yeah.
Okay,
What is the negative one?
it's gonna have to be negative because it's going down, yes. And I'm going to assume if you do not put a negative, like if you just write a number, that it's positive. You have to actually write the negative sign, or I'm going to assume that it's positive,
So
yes.
the only one that's negative is heat of reaction?
Yeah, the delta H, yes. The heat of reaction, or the enthalpy, which is the delta H.
So no matter what.
No, it's not always going to be negative. It's only going to be negative if your downhill slope is greater than your uphill slope.
Confused with what you mean.
Is this the longest downhill? Like, which is bigger, this side or this side?
I got you. I'll teach you this.
Like, I'm not trying to like, yes, yes. Okay, you're talking about which one? The top one? DNE. Heat of reaction is the difference between your reactants and your products. Okay, so that would be 30 minus 10. 20, which is negative. That's right. Your activation energy is the just. You did it right. This one is between the reactants and the products, so that's 50 minus 20, which is 30, and it's up. Okay. And your activation is your distance between 20 and 100. So that one's not right. Your activation energy is, it's how far it takes from your original start, whatever that is, to that hump. So it's the top of the hump minus the reactants, not zero. Wait, hold on, I so need to, let me do my attendance. Because George is here, Dylan's not here. Veronica was online, Declan was online. Awesome. Yes, and if you did yesterday's and you're done with today's, we're through. Because I just want to make sure that I'm giving you guys adequate time if you don't understand how to read the graph to troubleshoot it. There's seriously only 2 subjects on your next test. Today's, well, this stuff, and tomorrow's. It's not much at all. And like I said, it's not hard. It's just how well can you read a graph? Do you understand how to take lines to the left? Yes, I know with the dotted line, there's some human error that might be there. Do you have a question or will you finish? Which one are you asking about, the top one? Okay, so your reactance is 30, your products. You don't have to do -10 for your potential energy. The only thing that is going to be negative is the distance between, it's this, the distance between your products and your reactants. Okay, so your PER is right, your PEP is right. You just don't need to do -10. Your PEA is right. Your activation energy. Okay, so your delta H. Okay, so your delta H is from here, because you're going to go straight across with the reactants to your products. So this is your delta H, which is 30 minus 10. Okay, so you got that right. So that's -20. That's your answer for your delta H? Okay, so that's right. And then your activation energy is your distance between your reactants up to that hump. Did you not do that one? No, you didn't do that one.
So am I
But-
supposed to subtract those two?
It's not hard. It's not hard. Like I said, it's just a matter of teaching you. And I gotta pause the recording because we're not supposed to be saying students' names on Google Meets and stuff. Legality reasons. FERPA, honestly, FERPA.